Alright, this is the Math 2 unit review worksheet and for Unit 13. And first question is, what is a sample space? So a sample space is the set of all possible outcomes. Number 2, what is the sample space for a single roll of a 6-sided number cube? So the sample space would be 1, 2, 3, 4, 5, or 6. Number 3, draw a tree diagram and list the sample space for 3 coin flips. So for my first coin flip, I can have heads or tails. Second coin flip could also be heads or tails. Third coin flip could also be heads or tails. That should be a T. And so we there's our tree diagram, and our sample space could be heads, 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 tails, heads, tails, heads, heads, tails, tails. Gotta fix my tree diagram, sorry. Tails, heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. There are 8 possible outcomes in the sample space. 4 and 5 use a Venn diagram to display the following situations. So 4, a baseball team has 11 members that play infield position, 8 that play outfield, 4 that play both infield and outfield, and 22 players on the team. So I'm going to draw 2 intersecting circles, one for infield, one for outfield. I'm going to start with the intersection. They say that 4 players play both, so put 4 in the intersection. 11 play infield, so 4 we've already accounted for. So 11 minus 4 gives us 7. These would be only infield, so 7 only infield, 4 that play both. And then it says 8 play outfield, so I'd have 4 that only play outfield and 4 that play both. That adds up to 8. And so now we've accounted for 7 plus 4 plus 8, which is 15. But there are 22 players, so the rest of the players don't play infield or outfield. So it would be 22 minus 15, which is 7. For 5, we have business professionals who have flown in the past year for business, and those that have driven. And again, I'm going to draw 2 intersecting circles. We got flown and driven. Start with the intersection. 25 have both flown and driven for business. 95 professionals total. 40 have flown. So 40 minus 25 is 15. So 15 have only flown, 25 have flown and driven. That adds up to your 40. And 60 have driven. So 60 minus 25 is 35. So 35 have only driven, 25 have driven and flown. That adds up to 60. And now if we add all this up, 35 plus 25 is 60 plus another 15 is 75. So leaving 20 more to total our 95 business professionals. Number 6, refer to 4 above. How many baseball players only play infield? We see that 7 only play infield. 7, refer to 5 above. How many have neither flown nor driven for business? That would be the 20. What is the name for two events C and D where the probability of event C happening does not affect the probability of D happening? Independent. Give an example of two events that are independent. Getting a tail with a coin flip, and a 6 with a roll of a number cube. Those two events have nothing to do with each other at all. What is the name for two events J and K that cannot happen at the same time? Mutually exclusive. Give an example of two events that describe number 10 above, so mutually exclusive. So flip a coin once and get tails, and at the same time get heads. Can't get both at the same time, so the event of getting tails and getting heads would be mutually exclusive. They can't happen at the same time. 12 through 15, a bag contains 40 marbles. 14 are red, 8 are blue, 6 are white, 12 are green. Find the probability if one marble is chosen. Find each probability if one marble is chosen. Write your answer as a fraction reduced to lowest terms. So 12, what's the probability we get a red? Well, there's 14 red out of 40. And if we reduce that, we can cut them both in half, get 7 out of 20. Green, there are 12 green out of 40. So I'll reduce that. You could divide them both by 4 and get 3 out of 10. Blue or white, well, there are 8 blue and 6 white, and they're mutually exclusive, so we could just add them together. 8 plus 6 over 40. 8 plus 6 is 14. Cut them in half, you get 7 over 20. Not red. Okay, well, let's look at red. 14 are red. Well, actually, so not red would be the complement of 12, so it'd be 1 minus 7 out of 20. Which is going to give us 7 minus 20 is 13, so 13 out of 20. 16 to 18, Q and R are mutually exclusive, meaning they cannot happen at the same time. Or it means that the probability of them happening at the same time is 0, so that's 16. That's what mutually exclusive means. Because they're mutually exclusive, we can find the probability of Q or R by adding the probability of Q and the probability of R. So 0.62 plus 0.12, which is 0.74. Not Q or R. Alright, so for 18, let me make a little table to help you visualize this. So we have Q or not Q. We have R, and we have not R. So We said the probability of Q and R is 0. Probability of R, they tell us, is 0.12, so this is 0.12 here, because 0 plus 0.12 is 0.12. Probability of Q is going to be 0.62, so this is 0.62 here. The total here is going to be 1, so 0.62 plus, complements add up to 1, 0.38 adds up to our 1, and so that tells us this has got to be 0.26, and this one's 0.88. Okay. So if I want the probability that's not Q, I'm going to highlight the not Q. So that would be this piece is not Q, or it could be R. So that's what we're looking at, not Q or R. And so we're adding 0 plus 0.12 plus 0.26 and getting 0.38. To 21. We have independent events, and so I'm going to start with 21. Because they're independent, we can find the probability of D and E by multiplying the probability of D times the probability of E. So 0.85 times 0.4. 0.85 times 0.4 is 0.34. Probability of D or E is going to be the probability of D plus the probability of E minus the probability of D and E. So that'd be 0.85 plus 0.4 minus 0.34. And we get 0.91. And not D or E. This one I'll use a Venn diagram to help visualize. We could also use a table like we did in number 18, but here I'm just going to work with the Venn diagram. I know they're overlapping because the probability of D and E is 0.34. So we got 0.34 here. I'm using probabilities. The probability of D is 0.85. So let's say this is D, this is E. So if the probability of D is 0.85, 0.85 minus 0.34 is 0.51. So if I add those two, I get my 0.85. And the probability of E is 0.4, so 0.4 minus 0.34 is 0.06. And then that should add up to our 0.91. If I check that, 0.51 plus 0.34 plus 0.06 comes out to our 0.91. And so we're left with 0.09 out here. So now we want not D, so I'm going to highlight everything that's not D. So everything outside of D. This is outside of D, this is outside of D. So that's not D. Or it could be in E. Well, this is the other piece that it could be. So if I add those three up, I get the answer to 20. So 0.34 plus 0.06 plus 0.09, and I get 0.49. Number 22 to 30, we're to use the two-way table to find each probability. Acceptable answers include reduced fractions, decimals rounded to the nearest hundredth, or whole percentages. So 2, we want the probability of P and S. P and S. Sorry, E and S. So that would be the 140 over the 1000. We can divide top and bottom by 10 and get 14 over 100. And divide those by 2 and get 7 over 50. D or T. So if I want D or T, I am looking at this row D and this column T. So I'm highlighting the ones I want, and so I need to add those up. And I end up with 520 over 1000. And I'll reduce that, divide by 100, get 52 over 100. Cut it in half, 26 over 50. Cut in half again, 13 over 25. Next one is E or F. So everything here highlighted is E, everything here highlighted is F now. Add those up. We get 700 over 1000. Which reduces to 7 over 10. 25, want the probability of R or S. So R, I'm highlighting what belongs to R, highlighting what belongs to S. Add those up, we get 650 over 1000. Could reduce this to 65 over 100. And then we can divide 65 by 5 and get 13. Divide 100 by 5 and get 20, so 13 over 20. Probability of D and F. Well, D and F belong to the same column, belong to rows, and they don't intersect, so this is 0 because they're mutually exclusive. Probability of E. E adds up to 325 over 1000. If we divide 325 by 25, we get 13. And if you divide 1000 by 25, you end up with 40. So 13 out of 40. 28, probability of S given F. So we're going to look down F column right here. I'm highlighting it. It's a total of 375. So that's our denominator, is the total of F, which is 375. Sorry, that should be a 75. And just in that row, 180 belong to S. So it's 180 divided by 75. And so 180 divided by 5 is 36. And 375 divided by 5 is 75. 36 divided by 3 is 12. And 75 divided by 3 is 25. So 12 over 25. Number 29, we're looking for the probability of E happens given that R happens. So we're looking only at column R. Column R, we have totals 250, so that's our denominator. And just in that, 110 belong to E. Divide top and bottom by 10, you get 11 out of 25. And that's our answer. And then 30, we don't want it to belong to T. So that means it can belong to R or S. So the denominator is going to be 250 plus 400, which is 650. And then within there, you don't want it to belong to F. So that would be these 4 here that I'm circling. And so I'm going to add up 90 plus 80 plus 110 plus 140 and get 420. And then start reducing. Divide by 10. And then that's as much as it reduces, so 42 out of 65. Next, complete the table below for the sum of rolling 2 die. There's our dice. All right, and then 31, we're finding the probability that we get a sum of 6 or 10. So we just need to count up how many 6s we have and how many 10s we have. We got 1, 2, 3, 4, 5 6s and 1, 2, 3 10s, so 5 plus 3 out of the total, we have 36 different sums. So 8 out of 36. Cut those in half, you get 4 out of 16. Cut them in half again, you get 2 out of 8. Cut it in half again, you get 1 out of 4. Number 34, we want the probability that one die shows a 4 given that the sum is 6. So I'm going to go back to table here, and I'm going to leave the 6's highlighted because that's what we're looking at. We're looking at those only. So because it says given that the sum is 6 and we count, we got 1, 2, 3, 4, 5 cases, the probability is going to be something over 5. And so if we look at those 5 cases, which of those cases have one of the dice showing a 4? So here's a 4, so this case right here, that 6 would have a 4 and a 2. And then there's one more case over here with a 4 and a 2, so we'd say 2 out of 5. So that's number 34. Sorry, I'm going in a little bit out of order here. Number 32, we want the probability that the sum, we get a sum of 7 and doubles. Okay, sum of 7 and doubles. Well, if it's a double, it's going to be even. 1 plus 1 is 2, 2 plus 2 is 4, 3 plus 3 is 6. So you can't have a double that's a sum of 7. So that's impossible. Those are mutually exclusive events, can't happen at the same time. And so we're going to get a probability of 0 for number 32. And then number 33, probability we get doubles or a sum of 10. So the doubles, we have, I'll circle them. Okay, those are my doubles. And then here are my sums of 10. So I'm going to count how many I have. I got 1, 2, 3, 4, 5, 6 doubles, plus 2 more that are not part of that. So 7, 8 out of the whole 36. Which is going to give us, if you cut that in half, you get 4 out of 18. Cut that in half again, you get 2 out of 9. And I just realized I made an error in number 31, so I'm going to correct that. So it should be 4 out of 18, which is 2 out of 9. All right, on to 35. 35, we have a combination lock, has 4 dials, each with 10 digits. How many possible arrangements are there? Well, so to create a combination, you have 10 choices for the first dial, 10 choices for the second dial, and then for the third, and then for the fourth. And so using the multiplication or the addition, the fundamental principle of counting, we multiply these 10s together and get 10,000. 10,000 arrangements. 36, how many numbers can be made using the digits 1 to 4 with no digit allowed to repeat? So how many numbers? So you can create a 1-digit number. You got 4 cases, right? You got your 1-digit number. You got your 2-digit numbers. We can create a 3-digit number. Or you can create a 4-digit number. So it's important to consider these cases individually and then add those number ways up. So if we're doing a 1-digit number, there's only 4 ways, because we could 1, 2, 3, or 4. 2-digit number, no digit allowed to repeat, so we have 4 choices times 3 choices, which is 12 choices. 3-digit number, we got 4 times 3 times 2, which is 24 choices. And a 4-digit, you got 4 times 3 times 2 times 1, which is 24 as well. So the answer is going to be 4 plus 12 plus 24 plus 24, because those are the total number of numbers that we can make. And so we add those up. 24 plus 24 is 48, plus 12 is 60, plus 4 is 64. So 64 different numbers. 37, a girl wants to invite 9 friends to her tea party, but she has room for only 5. And how many ways can she make this choice? So here she just wants a group. Order does not matter, so this is a combination. Out of 9, she's choosing 5. So we could say 9 factorial over 9 minus 5 factorial times 5 factorial, which is 9 factorial over 4 factorial, 5 factorial. And you can work through this. 9 times 8 times 7 times 5 times, well, we could say times 5 factorial. And this is divided by 4 times 3 times 2 times 1 times 5 factorial. Cancel out the 5 factorials. 4 times 2 is 8. Just reducing this. 9 over 3 is 3. So we're left with 3 times 7, which is 21. But I'm noticing I missed my 6 in this fraction here, so I need to fix this. Should be 9 times 8 times 7 times 6 times 5 factorial. And so actually we get 3 times 7 times 6, and that's more than 21. It's actually going to be 126. So there's 126 ways she can make that choice. 38, a queue has 4 girls and 4 boys standing in line. How many different arrangements are possible if the boys and girls stand anywhere? Well, if they stand anywhere, you have 8. You have just 8 people lining up, and so you have 8 choices for the first person, then 7, and then 6, all the way down to 1. So this is the same thing as 8 factorial, and when you punch that into a calculator, you get 40,320. So there are 40,320 different arrangements if they stand anywhere. Second, part B, we want boys and girls to alternate. Well, there's an equal number of boys and girls, so there are 2 cases. The first case can start with a boy, so you can go boy, girl, boy, girl, boy, girl, boy, girl. And the second case can start with a girl. Girl, boy, girl, boy, girl, boy, girl, boy. So in the first case, if we just consider that one, how many different ways can we do that? Well, we have different slots where we can place a boy, and we have 4 different slots, and we have 4 boys. So in the first boy slot, we got 4 choices. In the second boy slot, we got 3 choices, and then 2, and then 1. And then for the girls, for the first girl slot, we got 4 choices, and then 3 times 2 times 1 in the same way. And so we get 4 factorial times 4 factorial ways. And 4 factorial is 24, so we got 24 times 24, which is 576 ways. We're going to get the same thing for the second case. 4 times 3 times 2 times 1 for the boys and for the girls, so we're going to get another 576. And so we got 2 576. If we add them together, or we could say 576 times 2, we end up with 1152. So there are 1,152 arrangements where boys and girls alternate. Part C, 2 particular girls wish to stand together. So let's call them girl 1 and girl 2. And I'm going to view that as one choice, one person. And then we got 2 other girls, and we got 4 other boys. So instead of having 8 people here, I'm going to see it as I got, in a sense, 7 choices. But this is case 1. Because the 2 girls that are standing next to each other can switch places. So we can also have girl 2 and then girl 1, and then the others still for choice. Okay. So the first case, we have 7 options, and then times 6, times 5, times 4, times 3, just like we did in part A. So it was 7 factorial. And then we have 7 factorial ways for the next arrangement. And so we're going to add those together, and so our answer is going to be 2 times 7 factorial. Using a calculator, this comes out to be 10080, so 10,080. Part D, next, all boys are standing together. So we can visualize it kind of like part C, but we got all the boys standing together. So we got all 4 boys. So say boy 1, boy 2, boy 3, boy 4, and then we have 4 girls. Okay, and so first of all, there are 5 choices. right? Well, who do I put first? I could put all the clump of boys together first, or I could pick one of the 4 girls. So you got 5 choices, and then 4, 3, 2, 1. So 5 factorial. But then we need to be concerned, well, how many different ways can these boys stand next to each other? Or how many different ways can you arrange 4 people in 4 places? And that's 4 factorial ways. So we're going to multiply 5 factorial times 4 factorial. And using a calculator, we get 2,880 ways. And then E, a particular girl, Mindy, does not wish to stand next to Carrie. So we want to see how many different arrangements there are where Mindy is not standing next to Carrie. Well, in A, we found out that there are 40,320 ways that 8 people can stand next to each other. And then in C, we found out how many ways 2 particular girls can stand next to each other. So if we subtract out those, we're left with the number of ways that these 2 girls cannot stand next to each other. So 40,320 minus 10,080. And we end up with 30,240 ways this can happen. (39) In a train, there are 8 seats with 4 facing the front and 4 facing backwards. If 5 people sit down in the carriage, how many different ways can they be seated if 2 of the people don't like sitting backwards, and how many ways can they be arranged? So sorry for this, but this is kind of, the wording here is weird. So here's the case. We have 4 seats facing 4 seats. So here's seat 1, 2, 3, 4. Let's call those front facing seats. And then 1, 2, 3, 4. And then you're in this carriage here. Maybe here's the door that people would walk in and sit down. And we have 5 people. And that are going to sit down. And 2 of those 5 don't like sitting backwards. So two of those people are going to sit in those first 4 seats. And so I'm going to start just by using the fundamental counting principle. The first person, let's say the first 2 people are the pickier people. They have to sit forward. So the first person that's sitting forward, he's going to walk in. He's got 4 choices. Let's say he sits right here. Okay. Second person walks in. That's another picky one. He's got to sit forward. So now he only has 3 choices. Let's say he sits right here. So now there are 6 seats left, and there are 3 people left. So the third person walks in and doesn't care where they're going to sit, so they have 6 options. Let's say they sit right here, and then the 4th person walks in. There's 5 options. Let's say they sit here, and then the last person walks in, the 5th person, and they have 4 options. Let's say they sit right there. So now all 5 sat down, and we can multiply these together to find out how many different ways this can happen. And we get 1,440 ways. Number 40, from a group of 9 people, how many groups of 5 may be selected so as to include the youngest or the eldest, but not both? So you got 9 people, and And so we're going to consider two cases. So we want to either include the youngest or the eldest, but not both. Well, the first case is if we're going to include the youngest, but not the eldest. So if we have I'll put young for youngest, okay? So in that case, and order doesn't matter, we're just selecting 5, but there's only 8 to choose from because we're not allowing the eldest to be part of this choice since the youngest is included. So there's 8 to choose from. It's a combination. We're choosing 5. The second case is when we include the oldest, but if we include the oldest, we can't include the youngest. So again, we still have 8 people we're picking out of. It's a combination because the order doesn't matter. We're still picking 5. So we're going to find these two and add them together. So our answer is going to be 2 times 8 factorial over 8 minus 5 factorial times 5 factorial. Okay. The fraction is the 8 combination 5, and I'm multiplying it by 2 because I have 2 of the same value that I want to add together, which is equivalent to multiplying it by 2. So this is 2 times 8 times 7 times 6 times 5 factorial. 8 minus 5 is 3, so 3 times 2 times 1, that's your 3 factorial, times another 5 factorial. 5 factorials cancel out. 3 times 2 times 1 is 6, canceling out with the 6. So now we have left 2 times 8 times 7, and 16 times 7 is 112 different groups. Number 41, find the number of different arrangements of the word mathematics that are possible such that it begins with an M and ends with an S. So if we're fixing an M in the beginning and an S at the end, we're taking 2 letters out of the mix. So let's say I've taken that one out and that one out. So all that's left now, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 letters left that we're going to mix up. And out of those 9 that we're mixing up, we have some repetition. We have 2 A's. We have 2 T's. So we're counting for the 2 A's here, the 2 T's. We have 1 H, 1 E, 1 M, 1 I, and 1 C. So multiply this together and we have our answer. So 9 factorial divided by 2 factorial, which is the same as dividing it by 4. And we get 90,720 ways that is possible. And these are distinguishable, meaning there's no repetition. Okay, B, we're going to now, M and S don't have to start, it doesn't have to begin with M, doesn't have to begin with S anymore. We're kind of starting free with the word mathematics, but we want the 2 M's to stay together. So in this case, we're going to put M and M next to each other and treat it like one letter. So we still have an A, T, H, E. We put these 2 M's together, so we already use those. Got another A, T, I, C, S. So those are the letters we're looking at. And so if we count this up, we got 1, 2, 3, 4, 5, 6, 7, 8, 9. Treat it like 10 letters, so 10 factorial with 2 repeating A's and 2 repeating T's. Using a calculator, 10 factorial divided by 4 is 907,200. That's how many ways we can do that. And then part C, the letters THE stay together. We need to decide, it's not clear, do we want it to stay in that order, THE, or can those be mixed up as well? Let's say they stay exactly in that order. So we have the word the in this arrangement. So let's consider that first, and then I can say what you can do to modify that if you wanted to. So we're going to keep the as the and move everything else around. So we're going to treat that as one letter, THE. So if we do that, then we count how many letters we have. So M, A, that's 2. The THE is the third letter. 4, 5, 6, 7, 8, 9. 9 letters. And what's repeating? We got 2 M's. We got 2 A's. And that's it. So the T's are not repeating because one of the T's is used in the word the, and the other one's kind of by itself. And so 2 factorial, 2 factorial. And we did this already in A, and we got 90,720. Now, if we wanted to modify this where the letters THE could be in any order, then we want to find out, well, how many different ways can we arrange that? We'd get 3 factorial, which is 6. So then we'd multiply the 90,720 times 6, and then that would account for that. But the way I'm reading it here is let's just keep it in that order, THE. Last problem. From a group of 6 boys and 4 girls, in how many ways can 2 boys and 2 girls be selected and arranged in a line? So we got 2 boys and 2 girls. And so first of all, let's see, how can we, if this were a word, how many different words could we make? For example, another arrangement could be boy, girl, or we could do boy, girl, girl, boy, and so on. And the way we figure this out is we're going to have 4 factorial, because there's 4 letters, divided by 2 factorial ways, which is 6 ways. So I could have kept 3 more after this, and if you want, you can list out those 3 other ways. Now each way we have some choices. So if say we do the boy, boy, girl, girl way, well, for the first boy slot we got 6 choices because there's 6 boys to choose from, and then 5 choices for the second boy slot. And so then there's 30 different ways we can arrange the boy, boy. And then for the 2 girls, well, we're choosing out of 4 girls, so there's 4 girls for the first girl slot, and then 3 girls for the second girl slot. And so just if I arrange boy, boy, girl, girl, there's 6 times 5 times 4 times 3 ways to do that, which is 360 ways. Well, then we're going to have 360 ways for the next one too, because there's 6 for the boys, and then 5 for the boy slot, and then 4 for the girl, and 3. So we're going to get another 360, and we're going to have 6 of them, right? So to see how many total, we're going to multiply the 6 ways with the 360. So 6 times 360 gives us 2,160 ways.